Our planet is a dynamic system, capable of breathtaking beauty and immense destructive power. Among its most formidable forces are hurricanes, massive swirling engines of wind and water. These storms are not merely weather events, they are complex natural phenomena. How do these colossal systems form? Why do some remain relatively benign, while others grow into catastrophic monsters? What can the relentless pursuit of scientific understanding tell us about their nature and our future? Today, we embark on a journey into the heart of these storms. We will explore their intricate anatomy, trace their powerful evolution, uncover the sophisticated methods used to detect them, and understand the critical steps for preparedness. Hurricanes begin their lives over warm tropical oceans. They require sea surface temperatures of at least 26.5 degrees Celsius or 80 degrees Fahrenheit, extending through a significant depth of water. This warmth provides the essential energy. As the warm ocean water evaporates, it rises, carrying vast amounts of moisture into the atmosphere. This moist air cools and condenses, forming towering thunderstorms. During condensation, latent heat is released, further warming the air and causing it to rise even more. These individual thunderstorms then begin to organize. Under the right atmospheric conditions, they can coalesce into a rotating system, a nascent tropical disturbance. This organization is a critical step in their development. The Earth's rotation plays a crucial role in giving these systems their characteristic spin. This phenomenon, known as the Coriolis effect, deflects moving air, initiating the counterclockwise rotation in the northern hemisphere and clockwise in the southern. Without this spin, a hurricane cannot form. From a mere disturbance, these systems strengthen through distinct stages. They begin as a tropical depression, then intensify into a tropical storm, and finally become a hurricane once sustained wind speeds exceed 74 miles per hour. Each stage marks a significant increase in power and organization. At its core, a hurricane is a colossal heat engine. It continuously converts the thermal energy from warm ocean waters into the kinetic energy of powerful winds and torrential rain. This process drives its destructive potential. The structure of a mature hurricane is iconic. It features a relatively calm, clear eye at its center, surrounded by the most violent part of the storm, the eye wall. This eye wall is where the strongest winds and heaviest rainfall occur. A hurricane's life cycle can span thousands of kilometers, traveling across vast stretches of ocean. It continues to draw energy from warm waters until it encounters land or moves over colder ocean temperatures, which ultimately leads to its dissipation. To better understand and communicate the threat posed by these storms, meteorologists use a classification system. The Saffir-Simpson Hurricane Wind Scale is the primary tool for categorizing hurricanes. This scale is based solely on a hurricane's sustained wind speeds. It does not account for other destructive factors like storm surge, rainfall, or the storm's overall size, which can also cause immense damage. The scale ranges from Category 1 to Category 5, each with increasing wind speeds and potential for destruction. A Category 1 hurricane, with winds from 74 to 95 miles per hour, can cause minor damage, such as downed power lines and some structural damage to homes. A Category 3 hurricane, with winds between 111 and 129 miles per hour, is considered devastating. It can cause extensive structural damage, widespread power outages lasting for weeks, and make entire areas uninhabitable. At the top of the scale, a Category 5 hurricane boasts sustained winds of 157 miles per hour or higher. These storms are capable of complete and catastrophic destruction, rendering most framed homes destroyed and leaving areas uninhabitable for months. Hurricanes classified as Category 3 and above are designated as major hurricanes. These are the storms that pose the most significant threat to life and property due to their extreme intensity. It is crucial to remember that wind speed is only one factor in a hurricane's destructive capability. Even a Category 1 storm can cause significant damage through storm surge, inland flooding from heavy rainfall, and embedded tornadoes. The scale provides a baseline, but the full picture of a storm's impact is far more complex. History is punctuated by storms that push the boundaries of what we thought possible. These record-breaking hurricanes serve as stark reminders of nature's raw power. Hurricane Wilma in 2005 achieved the lowest central pressure ever recorded in an Atlantic hurricane. Its pressure dropped to an astonishing 882 millibars, indicating an incredibly intense and compact storm. In 2015, Hurricane Patricia in the Eastern Pacific set a record for the fastest sustained winds ever observed globally. Its winds reached an astounding 215 miles per hour, making it one of the most powerful tropical cyclones in recorded history. Hurricane Irma in 2017 demonstrated incredible endurance and strength. It maintained Category 5 intensity for over 3 consecutive days, a feat rarely seen in the Atlantic Basin. This prolonged ferocity devastated multiple Caribbean islands. These strongest hurricanes ever recorded tested the limits of our forecasting systems and the resilience of affected communities. They provided invaluable, albeit tragic, lessons in storm dynamics and disaster response. Our ability to detect and track hurricanes has advanced dramatically thanks to sophisticated technology. These tools provide crucial lead time for preparation and evacuation. On the ground, Doppler radar systems are indispensable. They measure wind speed and direction within the storm, as well as the intensity of rainfall. This allows meteorologists to see the storm's internal dynamics. Doppler radar provides detailed insights into a hurricane's structure, revealing rain bands, the precise location of the eye wall, and even embedded tornadoes. This granular data is vital for short-term warnings. From space, a network of satellites continuously monitors the Earth's atmosphere and oceans. Geostationary satellites like GOES and polar orbiting satellites track every stage of a storm's evolution, from its earliest formation to its eventual dissipation. These satellites are equipped with various sensors, including visible, infrared, microwave, and water vapor imagers. They capture data on cloud movement, rainfall rates, sea surface temperatures, and atmospheric moisture content. The vast amounts of data collected by these satellites feed into global forecasting models. These models then predict a hurricane's potential path, intensity changes, and expected landfall, providing critical information for public safety. Satellites offer an unparalleled perspective, allowing us to watch the entire life cycle of a hurricane unfold from thousands of miles above. This global view is essential for understanding and predicting these complex systems. When a hurricane approaches, time becomes your most valuable resource. Early preparation can mean the difference between safety and disaster. The first step is to stay informed. Monitor official sources like the National Hurricane Center and local emergency management authorities for the latest advisories and warnings. Do not rely on rumors or social media alone. Know your evacuation zone and have a clear plan for where you will go if an evacuation order is issued. Do not wait until the last minute. Traffic can become gridlocked and shelters may fill quickly. Assemble an emergency kit with essential supplies. This should include several days' worth of water and non-perishable food, any necessary medications, important documents, and enough cash for emergencies. Secure your home by boarding up windows or deploying hurricane shutters. Bring in all outdoor objects that could become projectiles in high winds. Elevate valuables and important documents to protect them from potential flooding. During the storm, stay indoors in the safest part of your home, away from windows and glass doors. If the eye passes over, be aware that the calm is temporary and the winds will return from the opposite direction. After the storm has passed, remain vigilant for hazards. Watch out for downed power lines, contaminated water, and flooded roads. Do not return home until authorities declare it safe. As we speak, meteorologists are closely tracking Hurricane Melissa, a hypothetical storm forming in the Atlantic in 2025. Its trajectory and intensity are under constant scrutiny. Current forecasts suggest Hurricane Melissa has the potential for significant strengthening. Its projected path could impact several Caribbean islands and potentially threaten the U.S. East Coast. Residents in the projected path of Hurricane Melissa are urged to stay alert, follow all advisories from local authorities, and finalize their evacuation plans. Preparedness is paramount. This serves as a powerful reminder that hurricane season is far from over. Every year, these storms pose a serious threat, and proactive preparedness is the single most effective way to save lives and minimize damage. The future of hurricane science is a race against a changing climate. We are witnessing trends that demand our urgent attention and continued innovation. Warming ocean temperatures are fueling stronger, more rapidly intensifying storms. This means hurricanes can reach peak intensity much faster, leaving less time for preparation and evacuation. However, advancements in technology offer hope. Improved satellite networks provide more frequent and detailed observations. Artificial intelligence models are enhancing prediction accuracy. Drone observations are offering unprecedented close-up data from within storms, further refining our understanding. These innovations are crucial for better forecasting. Ultimately, while science allows us to forecast these powerful storms with increasing accuracy, we cannot stop them. If you like this video, please share and subscribe. Pulse Nucleum.